In this video, I would like to discuss two very important consequences of the mean value theorem. The mean value theorem just tells us that if you have a nice function, if it's continuous and differentiable, then at some point in that function, the slope of the tangent line is going to be equal to the slope of the secant line. That is, the instantaneous rate of change is equal to the average rate of change over the entire interval. There are two consequences from this. To set up the first one, I want you to think about a function that is just constant. On the whole interval a to b, wherever you're at, it just remains flat. It's at the same height. So it's a constant function. Maybe it's constantly 5 or 6 or whatever height it's at, it's always at that value. Then my question for you is, if you pick some point on there, what is the derivative at that point? What would the derivative at that point be? And, well, it's pretty clear that if this is a flat horizontal function, then my derivative would be 0. So if the function is constant, then the derivative is 0 everywhere in between a and b. What the mean value theorem tells us is it tells us it's also true the other direction. That is, my first consequence, which I'll call a corollary. Corollary just means a consequence. So the first consequence of the mean value theorem is on an interval, some interval a to b, say, if the derivative is always 0, then the function is constant. So you can see if it's constant, then the derivative is 0, but now I want to say the opposite is also true. If the derivative is always 0, then the function has to be constant. And intuitively, this probably makes sense to you, because if the derivative is always 0, it just means, well, you can't go up and you can't go down, because going up is positive derivative and going down is a negative derivative. So if the derivative is always 0, then all you can do is lay flat. But the mean value theorem actually gives us a way of showing this. And this is how we can use the mean value for this. What we'll do is just pick any 2 points you want to on this interval. So any 2 points you want. So maybe I shouldn't call that a and b, but pick any 2 points, and I need to give them some name. So maybe I'll just call these 2 points like alpha and beta. Pick any 2 points, alpha and beta. Then the mean value theorem says that if you measure this f of alpha minus f of beta all over alpha minus beta, it should come out to be your derivative, f prime, for some point in between, for some point c in between. But we know it doesn't matter which point you pick in the middle here, because all of them we are assuming has derivative 0. So that's always just going to be 0. But if that derivative is always 0, that means this function is always 0, which means the top of it is always 0, which means f of alpha minus f of beta is 0, but that means that f of alpha equals f of beta. Okay, so maybe I got kind of fancy with the alpha and beta here, but the point is the function at alpha must be the same height as the function at beta. And you can pick any points. Pick any point you want in here, and we can show the function must always have the same height. So this just gave us a way of saying that if the derivative is 0, then the function always remains at the same height. Not a particularly profound observation, but a significant one. That just reinforces the idea that the derivative being 0 means that the function is constant. There's a second consequence of the mean value theorem. I'll call it, again, corollary for consequence. And that's if two functions have the same derivative, then, well, it's not that the functions are the same, it's the functions are almost the same. F prime of x is equal to g prime of x up to, that could be offset by some constant, like a +2 or +3 or +17 or whatever your constant is. So first let me show you how we get this from the mean value theorem, and then I'll explain the significance of this. And I'm sorry, that shouldn't be the derivatives, that should be the functions. The derivatives are the same, so that means your the derivatives are equal, so that means the functions themselves are equal up to some constant term. So let's try to see this from the mean value theorem. Well, all you have to do is we can introduce some new term, say h of x, which I'll define to be f of x minus g of x. But then, that means my derivative, h prime, will be f prime minus g prime. And we're assuming that my derivatives are equal, so f prime minus g prime is 0. But we just said that if your derivative is 0, then your function is constant. So that tells me that h of x is constant. But remember, h of x is just f of x minus g of x. So f of x minus g of x is constant, which means that f of x is just equal to g of x plus some constant. Okay, let's try to see this in action. First off, this should make sense to us, because if you think of a function like, say, x squared, and then you just adjust it by a constant, let's say g of x is x squared plus 3, when you take the derivative, f prime of x, then it's going to be 2x, but that's the same as when you take the derivative of g prime of x. Why? Because taking the derivative, this constant piece dies, right? It goes to 0. It gets ignored. So thinking of it the other way, which is the statement of the corollary, if we begin with two functions that have the same constant, that have the same derivative, we have two functions of the same derivative, then those two functions must be equal up to them having a different constant. And this could have a different constant too. This could be maybe plus 17, but the difference between these two functions is just in the constant term. That's what this is telling you. If the derivative is the same, then the functions are equal up to some constant term. Let's think about what this is telling you in terms of the graph. So if I have a graph of something like, well, 17 is doing quite dramatic, so let me just think about the graph of the functions x squared plus 1 and x squared plus 3. X squared plus 1, this graph looks something like this. So here's x squared plus 1, and here's x squared plus 3. How do I get that? Well, it's just 2 more. So I just bumped the whole thing up by 2. So here's my graph. Try to draw the graph, got a little bit shaky. But here's the graph of x squared plus 3. So here are my two graphs. And the key observation is these two graphs are really identical, except one is just higher than the other. One's been bumped up 2. But if I look at any point on this graph, the slope at that point should be the same for both of them. So, maybe I didn't draw this perfectly, but if this graph is just the same graph, bumped up again a little bit higher, they have the same slope. So the derivatives are the same. The underlying functions are just different by some constant. Second important consequence of the mean value theorem. We'll be using this quite a bit in the videos ahead.